Today we're going to talk a little bit more about interval of convergence. Recall, we want to think about what's going to be left behind in the limit from the ratio test. The polynomial and radical factors only matter at the endpoints. At the endpoints of the interval of convergence, that's where the ratio test always just comes back 1, which is no conclusion. So we have to do something else. Exponential factors will adjust a finite radius of convergence if there is one, and it's factorial factors that could lead to 0 or an infinite radius of convergence. This is because we're thinking about what's being left behind in the limit from the ratio test before we take limit as n goes to infinity. The polynomial and radical factors, when we simplify the ratio test, the limit from the ratio test, will always have the same degree on top and bottom. And that's why we get that limit of 1. Because we'll have an n squared over an n plus 1 squared, or square root of n over a square root of n plus 1. And so as n goes to infinity, those are balanced out. And so the limit is going to be 1. The exponential factors will have something like an a to the n over an a to the n plus 1. And so that leaves behind a 1 over a in the limit from the ratio test, leaves behind a constant in the limit from the ratio test. And the factorial factors leave behind an n, because we'll simplify something like an n factorial over an n plus 1 factorial. And that will leave behind the n plus 1. We write the larger factorial until we get to the smaller factorial. So we're thinking about running a ratio test, but we're not actually having to write down all the details in the ratio test. The point of being in a math class is not to have to do any math anymore and just know stuff. So here's one that comes up when we start studying the ratio test. Here we're going to see factorial factors and how they balance out. We saw how the exponential factors balance out. The x minus a to the n part, that gives us kind of our baseline interval of convergence. Everything within 1 unit of a. If I want to adjust that, then I put exponential factors in, because the exponential factors will leave behind constants in our limit from the ratio test. If I have a 5 to the n on top and a 4 to the n on the bottom, then we're going to have a 5/4 left in the limit from the ratio test. And then when we solve for the absolute value of x part, we get 4/5 for a radius of convergence. So the exponential parts are balancing themselves out. This example is constructed in such a way that we can see how factorial factors balance out. So let's do a ratio test. So, well, let's think about what should happen. We've got a 3 in the middle of our interval. The power series, whatever else happens, definitely converges at 3. A power series will never diverge everywhere because there's a value of x that we can plug in that zeroes out all the terms. So the power series, this power series will definitely converge when x equals -3. Because that will make all the terms equal to 0. The question is, how big is our radius of convergence? There are factorials. Factorials could lead to a 0 or an infinite radius of convergence because these factorials will leave behind n's in our limit from the ratio test. If all I had was the 2n factorial on the top, then this would be simple. The terms don't go to zero. The series only converges, the power series only converges when x is equal to -3. If all I had was this n factorial squared on the bottom, then it would be simple. The power series would converge for all x, because the limit from the ratio test will have a 1 over n squared, n plus 1 squared in the denominator. And that limit will go to 0 regardless of the value of x. But now there's some kind of competition between these factorials. We need to see that play out in a ratio test. So let's take the an, in this case, an, or an plus 1. We're going to replace all the n's with an n plus 1. So I have 2 times n plus 1 factorial, n plus 1 factorial, and then 2 copies of that, times x plus 3 to the n plus 1. An is just as it appears. The important thing to remember here is the 2n factorial. What happens when we plug in the n plus 1? The n plus 1 has to get multiplied by 2. So this factorial is actually a 2n plus 2 factorial. So this we can simplify to 2n plus 2 factorial. Let's throw this into the ratio test and see what gets left behind. So here we are doing a ratio test. With the x plus 3 to the n, the usual thing happens. That's exponential, so n factors cancel out, leaving 1 factor. It's in absolute value signs in the limit, but it no longer involves n. So the x plus 3 to the n plus 1 over x plus 3 to the n will give us an absolute value of x plus 3 outside of the limit. That absolute value of x plus 3, that's the basis for our, that's the normal thing that's always left behind in a ratio test on a power series. The absolute value of x minus a. If there were exponential factors, they'd be out there with the x plus 3. So we got to see what's going to happen in the limit. Now, our strategy for simplifying, I'm going to write the larger factorial until I get to the smaller factorial. But instead of the smaller factorial at this n plus 1, I'm going to go for, I'm going to target it at this 2n, because that's where things are going to cancel. 2n plus 2 factorial starts off with 2n plus 2. Then we write 2n plus 1, and then we have arrived at the smaller factorial. And that will be able to cancel out with the 2n factorial down here. The thing to note with the n factorial and squared is that's 2 copies of n factorial. So notice in the order of operations, the factorial is first, and then we square the result. So we can write this as 2 copies of n factorial. And down here, I have 2 copies of n plus 1 factorial. Now I'm going to write the larger factorial until I get to the smaller factorial. And in this case, that n plus 1 factorial is going to be used to cancel out an n factorial. So I start writing the factorials down here. I've got n plus 1 times n factorial. And the second one is a copy of n plus 1 times n factorial. And then the usual thing with factorials and the ratio test happens. A bunch of the n's cancel out, but it leaves behind n's. So what's left over in the numerator is a 2n plus 2 and a 2n plus 1. And what's left behind in the denominator is an n plus 1 times an n plus 1. So the limit as n goes to infinity of 4n squared over an n squared. These factorials were balanced out. That 2n factorial left behind 2 powers of n, 2n plus 2 and 2n plus 1. The n factorial squared in the denominator left behind 2 factors of n, and n plus 1 squared. So this limit is what happens when n goes to infinity in 4n squared over 1n squared. The only important terms are the 4n squared and the 1. So this limit is equal to 4 times the absolute value of x plus 3. And if this limit from the ratio test is less than 1, that means we'll have absolute value of x plus 3 needs to be less than 1/4. Question. So that means we'll have a negative 2 3/4 above and a negative 3 1/4 below. We'll definitely have everything in between those values. We got to think about what's going on at the endpoint. So at this point, I have to think about what's going on at the endpoints, and we don't have any polynomial stuff to help us out. Normally what we would do is we would look at the polynomial stuff and see if we have convergent or divergent at the alternating side, or convergent or divergent at the non-alternating side. In this case, we don't have any of those polynomial or radical stuff. We've just got these factorials and the x plus 3 to the n. Let's see what happens when we plug in the endpoints. First, let's remind ourselves of what's going on when we plug in the endpoints. So usually what's going to happen when we plug in the endpoints is that at one endpoint, we'll have the non-alternating, where the exponential part is just a 1, usually. In this case, it's a 1/4 because we had a limit from, because the 2n factorial over the n factorial squared, that was giving us a 4. And then at the other endpoint, we get the alternating version. In both of these cases, the limit from the ratio test is going to give us a 1. We're getting a 1/4 from the exponential part and a 4 from the 2n factorial over n factorial squared. So at both of the endpoints, limit from the ratio test is giving us 1, because that's always what happens at the endpoint of an interval of convergence when we run it through the ratio test. That's why we have to call out separately, check the endpoints of the interval of convergence. So at both endpoints, limit from the ratio test is going to be 1, which means we have to do something else. But we have this factorial stuff and exponential stuff, and ratio test is best in these situations. So what do we do if there's no polynomial radical? This seems like a question that I should be just about to answer. But in my mind, I did the messy part, which is the easy part. I simplified the ratio test with this 2n factorial over the n factorial squared. So that's the question that I'm not going to be answering today. Let's move things around a little bit. It's funny, one of my complaints, whenever you complain about other people, you're probably complaining about yourself. If you don't know the other person, you just see a stranger do a thing, you start thinking things about that person. And that reveals a lot more about you than it does about that other person. Because you're not actually privy to what's going on in their heads, explaining their actions, right? So you just make something up, and it's probably something that you don't like about yourself, but you don't want to admit, so you see it in other people. So what I realize is that a lot of times I will leave open questions like this because I've done the mundane part of the problem. I got you through like the boring part of the problem and how those factorials interact in the ratio. And then when it comes down to something where the stuff that we're supposed to be doing stops working, that seems like it when it should be my time to step in and say, let me save you from this question. I say, here's this question. It doesn't fit with what normally happens. I should reassure you that things are okay and answer this question. And then I don't. Like I never do. I always leave it as an open question. But then I realized one of the things that I dislike about Game of Thrones is something that I dislike about myself. I will forget that I raised this question and then just wander off into something else. Then at the end of the series or the end of the semester, I realized how many plot threads I opened up and then just let go. Set a bunch of stuff up, don't do anything about it. You know what I mean? Anyway, that's the question that you should be thinking about. What we're trying to do is learn how to read what's going on in a power series. So here, I'm going to change the center of this series because I should highlight the other thing that I changed. Maybe I should leave it at +3. The important thing is that the n factorial in the denominator is not being squared. I want to think about what happens if the denominator is not squared. What's going to happen if I don't square that factorial in the denominator? So now I've got a factorial over another factorial. In the previous example, we saw those balance each other out to 4. What if I flip things over and put the n factorial squared in the numerator? And what if we run the 2n squared into the denominator? What if this is what our power series looks like? All right, 2n factorial in the denominator. What if the 2n factorial is in the denominator? What if the 2n factorial is in the denominator and there's only one n factorial in the numerator? So we started off with that 2n factorial over n factorial. And we saw what happened in the ratio test. Now we want to figure out what's going to happen in the ratio test if I start making small changes, because we need to learn how factorials balance each other out. So think about what's going to be left behind when we do a ratio test. Remember, we always get convergence at the center. So this first one here definitely converges when x is equal to 5. What we're trying to figure out is where the left and right endpoints are going to be. In the second example definitely converges at the center of the series when x is equal to -7. And in the third example, definitely converges when x is equal to 1. But we need to know about the radius. How are these factorials going to tell us about the radius? Our normal radius, if those factorial factors weren't there, our normal radius is 1. And then that would be our finite radius. And that usually comes from our exponential stuff. So how are these factorial factors going to interact to adjust the radius of the curve? All right, these are the 3 that I want to know about tomorrow. These weirdly contrived power series to explore what's going on with factorial factors in the ratio test. Tomorrow we'll talk a little bit more about where power series comes from. But that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.